Bismillahirrahmanirrahim. Electromagnetic field theory, and today our topic is charge distribution along the line, the surface, and the volume. Okay, so this is the example of the point charge. We have only one charge, and this is the field around this point charge, and these are the charges distributed along the line. It may be along the x or along the y or along the z. So this is the this is the surface charges. So we have now the two lines or two axes will be involved in surface charge, either xy or yz or xz. Similarly, for the volume charges we have the three axes x y z. All the threes will be involved in volume charges. Okay, so in previous lecture we have studied the electric field intensity, which is defined as mathematically the force applied on a unit positive charge. So applying the Coulomb's law, we have k q1 q2 over r square. So replacing the F from the Coulomb's law in this equation, we will have K Q Q1 Q1 Q over Q R square. So and the test charge of the Coulomb's formula and the test charge of this E formula will be cancelled out with each other. We will have KQ over R square. This is actually the R, capital R. Okay. Okay, and this R is actually the distance between the mm, test charge and the source charge and the test charge. Okay, and this Q is actually the source charge, while the test charge has been cancelled out with this test charge. So we will have the formula E is equal to K Q over R square, and for the direction we will use the R unit vector, because the electric field intensity is always directed along the R. Okay, so um, as we know that R unit vector is equal to R vector over R magnitude. So replacing this R unit vector over here, so we'll have E is equal to K Q over R square and R vector over R absolute. So this is also the magnitude, this is also so the bases are the same, so their power will be added. So we will have R cube K Q R R vector over R cube. So this is the final formula for the E, and if you want to replace K value, so you can also do it. K is equal to 1 over 4 pi epsilon naught. So 1 over 4 pi epsilon naught K R vector over R cube absolute. So this is the formula for the E, and we will use this E formula in the line charges and in the surface charges and in the volume charges. Okay, so uh, let's move on to the line charges, the surface charges and the volume charges, and we will using this derived formula. Okay. Okay, here we go. The line charges, the charges are distributed along the line L. Okay, and the surface, the line charge density is the defined, mathematically defined as the charges distributed along the line L. Okay, so now first we will take the small portion of dl, and then we will apply the integration at the end to assume the whole length charges. Okay, so uh, have a look to this vector. This is the point of observation, these are the source charges, and this is the origin, because the source charges are apart by r1 distance, while the point of observation, where the point of observation means here we have the test charge. So the test charge is replaced is apart from the origin by a distance r, and a capital R is the position vector or the distance between the source charge and the test charge. So uh, R1 from origin is directed from origin to source charge, and R is directed from origin to test charge or point of observation. And the direction of R is always from the source charge to the test charge, because it will push the test charge. Okay, so consider this small length dl, and in this small length we will have small charges dq. So according to this formula, rho l is equal to q over dl. For the small charges we have the dq, and for the small length we will replace it by small dl. Okay, I have mentioned these variables over here. So uh, um, by cross multiplication we have dq is equal to rho l dl. So we will use this equation later on. Okay, applying head to tail rule on this diagram, this vector diagram. So r1 plus r1 plus r is equal to, this is the resultant vector r. Okay, so but we are in need of this we are in need of this r. So r is equal to r minus r1. Okay, so uh, according to this equation, E is equal to q over 4 pi epsilon naught r vector over r cube absolute. I've already told you that we will use this equation again and again. Okay, so keep this equation in mind. So replacing this r by this, so r is replaced by r minus r1. These are the vectors. Okay, as you can see from here. So r minus r1 divided by r minus r1 absolute whole cube. Okay, whole cube. So you can use this equation and replace dq by rho l dl. So in order to introduce the line charges, so as dq is equal to rho l dl, so E will be equal to dE will be equal to rho L, replacing the dq value. So rho L dl r minus r1 over 4 pi epsilon naught r minus r1 absolute whole cube. Okay, so for considering the whole charges, so we will apply the integration for this dl, and this dl will be from 0 to l, means the whole length is considered. So due to this whole length, the whole charges will be automatically uh, collected. Okay, so rho l, this is the rho l, dl is the integration. So we will write over here r minus r1 divided by r minus r1 whole cube. So this is the electric field intensity for the line charges distributing along the long line l. So similar is the case with the surface charges. We have surface charge density mathematically, rho s is equal to q over s. Okay, so uh, taking the small surface as we have taken in the line charges. So the small charges will be r, this is the position vector from the source charge to the test charge. And here again we have considered that the source charges are apart from r1, while the test charge is apart from the distance r. So again we will apply the head to tail rule, and we will have r is equal to r minus r1. So according to this formula, taking the small fraction of the surface, so rho s is equal to dq over ds. Okay, so dq is equal to rho s ds, and again keep this as equation number one, and we will replace this dq by this later on. Okay, so dE is equal to dq over 4 pi epsilon naught, again r minus r1 vectors over r minus r1 whole cube. Okay, so but this is the E in term of dq, so we need to find the E in term of surface charges as we have done in the line charges. So d is equal to rho, replacing the dq value. This is the dq value of the previous slide. So rho s ds r minus r1 this. Okay, now applying the integration. So this integration will be actually for the whole surface, to consider the complete surface, not the fraction of the surface but the complete surface. So rho s r minus r1 over r minus r1 whole cube. Okay, and I have written it by hand with different colors, so for your convenience and for your interest. Okay, now again we are switching to the volume charges. So mathematically the volume charge is rho v is equal to the charges distributed along the volume. This is the whole volume v, but now we will take only the small portion or small fraction of the volume dv, and the charges distributed along dv are dq. So oh sorry, this is actually dq. So dq is equal to rho v dv. Okay, and again this is equation number 1 and we will use it later on. Okay, so now what will be the value of E? De is equal to dq. Again that formula which I've already told you that we will use it again and again. So dq r minus r1 over r minus r1 whole cube, absolute cube. Okay, and this is the value of k. So in term of again this is the equation in term of dq. So we need to find the de in term of volume charge density. So replacing dq by rho v dv from the previous slide. Okay, and r minus r1 divided by 4 pi epsilon naught r minus r1 whole cube. Okay, so taking the integration on both sides in order to find the whole volume charges. So uh, rho v r minus r1, and this integration is actually for the dv. Okay, with respect to d for the volume, it means we have to put the limits of volume over there. Okay, so this is actually the general derivation. Now in numerical problems it will be more clear to you that how the different limits will be applied for this dv. Okay, so here we go, uh, taking the example of cylindrical coordinate system but for the volume charges. In this example uh, they've shown that the charges, we have a cylinder, full cylinder, complete cylinder, and the charges are distributed along this whole volume of cylinder. So we have the volume charges is equal to minus 5 into 10 raised to the power of minus 6 e raised to the power minus 10 raised to the power 5 rho z cube a coulomb per meter cube. Okay, because volume charges. Okay, now it looks very confusing to you, but it's quite easy, that we have a rho and z in this. So we will apply the integration for the rho z. But before, okay, this is q along rho v dv. Okay, so we have to replace the values for the rho v and the dv. Okay, so for we have already discussed the differential volume for the rectangular coordinate system and for the cylindrical and the spherical coordinate system. So clicking in mind the differential volume for the cylindrical coordinate system. So we will have dv is equal to rho d rho d phi and dz. Okay, so replacing the dv by this, I've already shown my arrow, and this is actually the value of rho v, which is given. This is the given. Okay, so we have the volume charges. So we will apply three integrations because this is the limit for rho. This is the limit limit for phi, and this will be and the limits of the z will be put over here. Okay, so move on to next slide. Colorful background for you people. Okay, so first the limits for the z are given that are 2 centimeter to 4 centimeter, but in SI system we will use the limits for z in meters. So convert it into meters. We will have the limits from 0.02 to 0.04. Okay, and again the limits for the row is also given, that is from 0 to 1 centimeter. 1 centimeter means 0.01 meter. Okay, and we have the complete cylinder, so it means the for the complete cylinder the limits for the pi is always from 0 to 2 pi. Okay, these limits are not given, but we have given that we have the complete cylinder. So you should know that for the complete cylinder the phi limits ranges from 0 to 2 pi. Okay, so these are the limits for z, for phi, and for rho. Okay, so in this equation we have no phi, so it means we have 1 for the d phi. So it is simpler comparatively, so we will solve this integration for the phi first. Okay, so phi phi means 1, the integration of this will be phi, replacing the limits of 0 to 2 pi. So we will have 2 pi minus 0, so 2 pi. So as this is the constant value, so shifting it outside the integration. Okay, and merge with this value. This is also constant, so taking it outside the integration so that the calculation is going to easy. Okay, now we will have the row e raised to the power minus 10 5 rho z. This is also in the power. Okay, so we will have rho and dz. Two, these two are mixed up. Look, in same variable we have rho and z. So we will solve it one by one. Okay, so move on to the next slide. Okay, now these are the constant values that have been shifted outside the integration, and now we are dealing with rho and z. Okay, so first of all they have solved the value for the z. Okay, this is this z, integration for z. So e raised to power minus 10 5 rho z. So uh, for integration with respect to z, we will have this in the denominator as well, minus 10 raised to the power 5 rho. Okay, and the limits for z, lower limit 0.02, upper limit 0.04, replacing it the upper limit, this is the upper limit, this is the lower limit. So we will have two functions. Okay, for the upper limit and for the lower limit. Now uh, now it is the term for the integration of rho. So rho, we have to apply the integration for the rho. Okay, so minus 4000 rho over minus 4000, because it's the integration for the rho. Okay, and applying the limit for this 0 point from 0 to 0.01, and separately for this variable we have e raised power minus 22,000 rho divided by minus 2000. Okay, and again from 0 to 0.1. So now replacing this over here and 0, so then we will have four values, one for this, 1 2 3 and 4. Okay, so replacing minus 4000 e raised power minus 2000 and e raised power 0 and e raised power 0. So from calculator we will have the value minus 0.025 pi as it is pi, and nano means 10 raised to the power minus 9. So this was all about the volume charges in cylindrical coordinate system. Now we have another example, example 2.4 of the book, and this is the drill example actually. Okay, so D, and in this example we have three parts, A, B and C, and again this is example for the volume charges, volume charges, volume charges and volume charges. Okay, so but now this is the we have the X, Y and Z. So X, limits for the X minus 1 to 2, limits for Y 0 to 1, and limits for Z 3 to 3.6. Okay, in B example we have the function is given in x y z, but there is a trick involved in this B part, because the function is in term of x y z while the limits are given for the row phi and z. Okay, so row phi and z, so we have to convert this xyz into row phi z later on. Okay, and in part C we have the function in term of r, theta and phi. So what does it mean? It means spherical coordinate system, and the limits we have to limits the of the whole universe. Okay, for the complete universe. So uh, let's move on to the solution of part A first. So as we know that q is equal to rho v dv. Okay, so as the function is in xyz, so we will use the differential volume for the rectangular coordinate system dx, dy and dz. Now the function, this 10 z square e to the power minus 0.1 x sine pi y dx dy and dz. It's look very confusing, but it is quite easy, because we have the separate equations, variables. This is for the z, and this is the function for the x, and this is the function for the y. So apply the limits of z for this variable, and for this variable apply the limits of y, and for this variable apply the limits of x. So there is nothing to worry about. Okay, so separately one by one, first they have solved the x. Okay, so this is the x variable e raised to the power minus 1 x, the integration for e raised to the power minus 1 x e raised to the power minus 1 divided by minus 0.1. Okay, replacing the limits 2 and minus 1, so we will have this. Okay, now this is again we will have a constant value for this. So taking it sorry this value, so taking it to the outside, so that the calculation is going too easy. Now it's the turn for the y, so apply the limits for the y, and keep the z as it is. Okay, so uh, the integration of sine pi y is minus cos pi y over pi, and the limits are from 0 to 1, so replace it by 1 and 0, so we will have minus 2, again taking it outside. Okay, and merge with these values. Okay, now it's at the last, we have to solve the integration for the z. So z square, integration of z square is z cube over 3, replacing the value 3.6 and 3, and after solving this, merge with these outside values, and we will finally we will get 119.48. So it's quite easy. Okay, integration for the respective variables. Now this is the B part. I've already told you while we were starting this numerical, that there is a trick involved in B part, and the trick is volume charges are given in XYZ form, but The limits are given in rho, phi, and z. So we have to convert these limits into this variable x, y, z into rho. So as we know that x is equal to rho cos phi, we have already discussed it in the class, and y is equal to rho sine phi. Okay, so replacing this x with this and replacing this y with this, so we have the rho and rho, so rho square, the 4 is already present there, and for the cos we have the for the x we have the cos phi, so this is the cos phi, and for the y we have the sin phi, so sin phi, and the RCS and CCS z is equal to z, so there is uh, nothing to convert for the z will remain as z. Okay, so now we have the variable of rho. These are the variable for the phi, and these are the so it's very easy. Apply the limits integration of z with respect to this. Apply the integration for with respect to d phi, and putting the limits of phi, and apply the integration with respect to a row, and replace the limits of apply the limits of row. Okay, so but first we have to replace this is actually the dv for cylindrical coordinate system, and this is the value of rho v from here. Okay, rho v from here, and this is understood that for the cylindrical rotation, the differential volume is rho dz d phi and d rho. So now this rho will be merged with this rho, so we will have the rho cube. Okay, so move on to the next slide. First of all, rub the previous discussion. Now it's easy for taking it to outside. A row square was multiplied with the row, so we will have a row cube. Cos phi sin phi. Okay. Okay, so uh, applying the limits for the z first. Okay, so z square, applying the integration z cube over 3, 0 to 3. Okay, so taking it to outside. Now it's the term for solving this. So as we know that 2 cos theta sin theta is equal to sine square theta, but now we have the deficiency of 2, so in order to introduce the 2 over here, we have to divide the 2 as well. Okay, so this is replaced by sine square theta, and the 2 was there, which we have divided for fulfilling the deficiency. Okay, so now applying the integration, sine square theta, sine square phi, sine square phi minus sine, limits, applying the limits. Okay, so sine square pi by 2 minus sine square 0. Okay, so this actually cos formula 2 sine theta cos theta. Okay, so now finding the values by using the calculator, we will have 1 from this side. This is actually 0, this is 1, so we will have 1. Now at the last we have to apply the integration for the row cube, which is actually a row 4 over 4, and the limits are from 0 to 2. So in the next slide, we will have integration applying the limits, and we will get 72 coulomb finally. And now the third part, which is very easy again. Actually, when one function is independent of the other function, then it is very easy for you to solve. But if one variable is dependent on the other, so now then it is a difficult task. Okay, so but in this case we have row v given, and we have to take the limits for the universe. Okay, so universe, the limits for the universe are r from 0 to infinity. For the complete sphere, we have theta from 0 to pi, and phi 0 to 2 pi. We have discussed this in the class, But for the universe, for the sake of universe, we have to apply the r from 0 to infinity to cover the whole universe. Okay, so and the differential volume for the spherical coordinate system is r square this. Okay, so replacing rho v and dv in this, we will get rho v dv. Rho v is here and dv is here. So before starting the integration, do some simplification, because the r square can be cancelled out with r, so we will cancel out this with this. Okay, so we are left with this 3 pi cos square theta sine theta and this and that. Okay, so first solve for the r. So we will have 1 over r square plus 1. So now again, you have to you should be sound with the trigonometric formulas of metric and FAC. So 1 over x square plus 1, the integration of 1 over x square plus 1 is equal to tangent inverse x. So now we have r 1 over r square plus 1 tangent inverse r from 0 to infinity. Okay, so replacing these values, we will get this. Now solve for the theta. This is actually the values for which we get from the r. Okay, integration of r. Now phi and theta. Okay, so first of all, we have to solve the values for the theta. So uh, again, using the trigonometric formula, so we will get this. Okay, replacing the value of pi and 0, so we will get minus 2, and replacing it, shifted it to outside the integration for the simplification. Now using the reduction formula, so we will get 1 0 to 2 pi d phi, replacing 2 pi minus 0, we will get 2 pi minus 0, and solving this, so we will get 15 minus 5. Okay, this is actually the reduction formula. Okay, so you can take the help from this. This is actually the repeat question. The C part is repeated by some another method, so have a look of this. So that is all about the first lecture. Now we will start the second lecture after a while.